Whoops. Get that thing. All right, we should get started. We were talking about memory, and we had gotten through the standard model. We improved on the standard model a little bit, maybe with the idea of working memory to stand in for short-term memory, which seemed like a kind of under-specified idea. And now we're going to explore the long-term memory aspect of this model. And this seems to be maybe the most important part of memory for kind of general purposes. So there have been a number of movies and maybe even TV shows which have kind of riffed on the idea that you are your memory. So imagine, as I think some of these movies had suggested, that your memory has been altered by some nefarious person trying to make you somebody you're not. And so your memories aren't your memories, but they're memories that have been planted there. And you think this is you, because you can remember, as you always could, back into your life. And everything about you kind of rides on that. Right? So there's one really bad one, Arnold Schwarzenegger, called Total Recall, which is really, really bad. And then there's some more recent ones which are kind of more the life whose names I'm not remembering. But anyway, so they're taking advantage of this idea, and it's an interesting idea. And it sort of tragically shows up in everyday life with people with dementia. When their memories start to go, they don't go in that kind of dramatic way usually. But the deficits that they start to exhibit they show up in places you wouldn't expect and are serious in ways that you wouldn't expect too. So, for example, you might lose what's called perspective memory, which is the ability to remember what it is you intend to do. And it doesn't sound like it should be too bad, except that if you put something on the stove, your perspective memory has in it this little, call it a trace or a marker, which says in a few minutes, go check on that darn thing on the stove. And if that doesn't happen, of course, bad things occur, right? So the thing on the stove, completely melts, or the thing in the microwave, just goes on and on and on. You don't turn it off. Right? So things like that, but also things like how to get places, how to operate a machine, how to solve a problem. Those are all functions of memory too. And when you have people with dementia, they tend to start to forget those things. And so very capable people become increasingly less capable and even dangerous to themselves and to others. So this is, for the most part, all of those problems are problems of long-term memory. So long-term memory are these very long-lasting representations about pretty much anything you can think about in the sense of facts, images, thoughts, feelings, skills, experiences, right? Anything that you can imagine holding in memory that persists as long as your lifetime, we think. Okay, which isn't infinite. Sorry, you already knew that, but people tend to forget, right? So it's not an infinitely long memory store temporally. It's not infinitely long, but it's as long as your lifetime. And that's pretty long. Good. You don't really need it beyond that anyway. So you don't think, at least. Right. So that's an amazing fact that memories last as long as your lifetime. The capacity is practically unlimited in that, as far as we know, there's no evidence of memory traces expiring, of them reaching their limit in terms of how useful they are. They are always there. You could, in theory, get to them, and you could just keep adding to them, right? So capacity of the system, that is how much memory, how much stuff it could hold. What we might think about is how much information it could hold, how many bits of information maybe, would be unlimited. Now, it's not a true infinity, right? Because you don't live forever. So you don't have an infinite exposure to information. So it's not really infinity in the formal sense. But it's a practical infinity for us. It's more than you could ever exceed. Right? So that's kind of nice. So there have been some estimates made. So people do these things. I'm not sure why. But so way back in the day, I guess now, Landauer estimated that there were 1 quadrillion bits of memory possible. The memory storage was that big. That's a big number. So big it doesn't really matter, right? I mean, if it were 100 billion versus a quadrillion, it doesn't matter, right? So a very, very large number. You can think about this number as 100 terabytes of information. So, try to convert that to something more concrete. So a very high resolution movie would be about 20,000 movies. So we have these two things: capacity, that is how much can it hold, and then duration, how long will it hold it for. So here we have these really great answers. Capacity, pretty much unlimited. For all intents and purposes, unlimited. And then duration, pretty much unlimited, at least for a biological creature who's only going to live for so long. It's going to last for your lifetime. All very convenient, right? So those are very nice and kind of incredible facts about long-term memory. There is a huge amount of work on what it means to have a memory trace in a physiological way. What is this thing that somehow points to something that happened in the past? What could that be? It's a very weird idea that somewhere in your brain, there doesn't seem to be any question, it's got to be in your brain someplace. All right, there's this thing, this chemical change, this structural change maybe, that is sitting there, and it, to you, points to something that's in the past. Right, it's just got to, like, write down the equations for that. No idea. Where do we even start? So the idea of a memory trace is a very weird idea, and it's not one that people doing memory just are kind of looking for evidence that something has changed, but how it could point like that. See what I mean? Like, you see what I mean by the pointing part? It's like, it doesn't just have to be like a change. The change has to be meaningful to the creature about a thing in the past to be a memory. Or maybe it's predicting something in the future, like from learning, but that's just as weird, maybe even weirder. Right? So that's seems like we've got something wrong there. Like something in how we're thinking about it isn't quite said correctly yet. Okay, but this is how we talk about memory trace, and I'm supposed to be teaching you about what we currently are thinking. So this is how people think about it. We tend to think about memory traces as being, as they're formed, new memories. They're representations of something new, a new pointer. This desk is here. Okay, got that. Somehow something has changed in my mind, and there's a memory trace there now that says desk there. Couple of options that are popular right now. One is that a presynaptic neuron becomes more effective in sending signals to its downstream neighbors. So maybe it now is going to release more neurotransmitter when it receives its own stimulation. So that would be one way to do the encoding. Get that property changed. We could also have a postsynaptic neuron become more effective at receiving signals, right? So you could either have the pre or the post sitting on either side of the synapse become better at what they do. So sometimes this could be sensitivity to the neurotransmitter, and that is called long-term potentiation. That is, it's now for some long period of time, it's more ready than it was before. So these are some hypotheses about how this might work. It's also possible for us to have a new synapse, totally new synapse be created because, let's say, the dendrites grow. Right, so some dendritic spine becomes a little bit longer. And, and now it makes contact with somebody new. It's a new synapse. Right, and that also could be a new memory trace. So you can imagine people in the lab are doing this kind of work. They're working with animals, usually mice and rats, and they're trying to do like single cell recording on maybe a living animal, or maybe they're doing post-mortem histology on neurons, saying, well, this creature just learned something new, and we see this, we think we see a change here. And so that's how it's done, right? You can see that the almost philosophical implications of, well, how does that change relate to what's going on in the world? Kind of not their business, right? They're like white coats in the lab, right, on the creature. But it doesn't mean the other thing isn't important. Okay, so there doesn't seem to be a single memory store. By that, I mean, there's not like one place that your memories are. That would have been a way to do it. Maybe you could organize the system that way, like your computer does it that way. Right? The hard drive, that's it. Right there. There's no memory trace sitting in the keyboard, as far as we know. Not much, at least. Keyboard kind of wears out. Maybe that's some memory, but not very effective memory. Right. So there's no single place for there to be a memory store. Rather, memory is all over the place, it seems. So when you try to retrieve something, your whole brain is active, which is also because you kind of have this idea that you're going to get thing, right? A memory that's a tape. My grandmother's apple pie. It's a thing, right? But my grandmother's apple pie apparently is all over my brain. So the hope is that there are going to be areas of the brain that are more or less specific to different types of information. So my grandmother's apple pie, well, that has a taste component, right? It has a kind of a texture component too, but it also has like an emotional component because, I'm there sitting in my grandmother's kitchen and she's being real nice to me. And so I'm feeling really good about myself because, with grandma, you can do no wrong. And out comes the pie, there's ice cream too. This is great. Right. So there's kind of an emotional area too, maybe someplace. Right. So the hope is that there are these areas and that they're all like feeding into the memory of this particular apple pie event. So that's how people are thinking about it in very broad strokes, of course. Maybe it could be improved. One thing that seems very clear is that we do move things into what we're calling long-term memory. And one of the ways we get it there, not the only way in, but one of the ways we get it there is through short-term memory or working memory, if you like that better. And the phenomenon that we're going to focus on for a little bit here is that the longer you work on something, the longer you have something in, we'll just call it short-term memory for now, the more likely it is to get shifted over into long-term memory. So there's the idea that we keep this kind of boxology where we have our three boxes, sensory, call it short-term and long-term, that being in short-term for a while starts to increase the probability of it making the jump over into long-term. Okay, so that's one way to think about it. Other people, and I'll just tell you to screw up a little bit, but not too bad, think about this whole thing as a bit of a metaphor. And they say aren't really three components. It's just like different ways of activating the network. And there's some advantages to thinking about it that way. But for us, we're going to think boxology. Okay, so box, short-term memory, I've got it in here for a while. Oh, it makes the leap into long-term memory. Now things are good because it's in long-term memory. And as long as I retain my ability to get that back out, I'm all set. Okay, so moving things into long-term memory. This is a very practical part of the course, as my memory researcher friends like to always tell me. They have important things to say about learning, about studying. So some of that will get woven into it. Okay? So how does information get into long-term memory? And how can it get organized so that you can get it back out? So I kind of suggested that you were like golden once you have it in there. Not exactly. But there's the other issue of getting it back out. Getting it in, that's hard enough. But then being able to find it in the right moment, right? That's always the problem, right? Having a lot of stuff is great. Finding it when you need it, that's the big trick. So how does information get in, and how can it be organized so you can find it? So here's kind of the distillation of the last 75 years of research on this. We're going to do it in like 2 slides. So information is thought to be stored in some form that can be accessed. That's the first idea. All right, so there's somehow, nobody knows what the code is, it gets coded up so that you can go and find it, right? So imagine trying to find something in the library, it's a good example, without the search structure that's in the library. Right, so obviously the analogy is the library is your memory, and your job is to find something in there. Okay. But there's no search help, right? You go to the little kiosk and you go, oh, I'd like to find, it's like, yeah, no idea who you are, I'm not talking to you. Right? At that point, it might as well not be in there. So without the search function, it's just, a place to have coffee. So that your brain is kind of the same way. If you can't find anything in there, it's not coded up correctly, you can't find anything because there's so much information. That's the metaphor, right? But here their promise is that it's coded so that it can be readily accessed. So these guys wanted to say that the manner in which you do the encoding matters tremendously. And so it's a theory of memory that isn't really so much about the physical act of moving something into a new memory store. It's more about how you link up what goes into long-term memory with what you may in the future encounter as what they'll call cues, but we'll just call like the world. Okay, this will make more sense in just a minute, I promise. So the accessibility of memory, this is again, these are like the big lessons from all this work. The accessibility of memory depends on the way that it got in, on the manner of encoding. And I'm going to rush this just a tiny bit so that we get to where it starts making sense. So we can talk about these 2 different broad types of encoding processes. And then we're going to break that down a little bit further. So one broad class of encoding processes are automatic. They don't require attention. There's no strategies involved. The whole thing happens without your awareness generally, and without your attempts to remember anything. So you're just encoding as you go, and for whatever reason, automatically it's getting put into long-term memory. The other side are effortful encoding processes, where you have intentional and controlled, you can think about it as movement or repositioning of the information into long-term memory. So studying is a great example of effortful encoding. Okay. Reading would be an example of automatic encoding, where you may not, you're just reading for pleasure. You're not trying to remember any of this. And yet you find that indeed the first, few passages of the Iliad have stuck with you for, or maybe they haven't, but, or something about a movie or maybe a song, right? It's not like you're trying to remember, the songs from Hamilton or something, and you can't get it out of your head. It was automatically encoded. So that's not helping us very much yet. Let's make it into a little bit more, a little more precise. So they've developed this idea called levels of processing. Okay, so think about levels of processing as kind of how you're dealing with the information, and how you're dealing with the information puts you on this kind of continuum of automatic to effortful, and also on a continuum of what they're going to call shallow to deep. And those will be a little bit more useful than automatic to effortful. So levels of processing at the deepest level, you are making that information hook into the new information, hook in the things you care about deeply, things you believe, things that are crucial to you, things that are like the bedrock of your belief system or something. Okay, so that would be like really deep processing. At the shallow level, you might just be making judgments about the font that something's written in, and the content of the word itself would be incidental. Right, so for example, like the example I just gave, at a shallow level, it's just structural. It's just the stuff that has to do with, the trivial details of how things were presented. And then at the other pole, deep, we're really into the semantic level where the meaning of things is important. And again, the more meaningful to you personally, the better the processing. So one consequence of this way of thinking, and it seems to be borne out by more practically focused research, is that the more you try to elaborate and actively think about information while you're trying to learn it, the more likely you are to be able to recall it when the time comes. So let me give you an example which is tied into some of this research. So let's say that you are supposed to remember words as they come up, and you're going to do so under various and sundry conditions. And we'll use an example of this one word, train, but it would be part of a regular long list of words to remember in a regular kind of a memory experiment. All right, so train. So one way in which you might try to control processing is you present a word and you've already pre-specified what it is that the subject's supposed to judge about the word. And then later, in a little bit sneaky way, you might hit them with an unexpected recall task. So they're not trying to remember, just messing around with their level of processing and seeing incidentally how much they remember. So I'm flashing these things up on the screen at you, and your task in the shallow condition is to judge whether the presented word is capitalized. And this is an example of shallow processing, because I don't even really need to process the word completely for that. Just like, oh, yeah, that's capitalized. Next. Nope, not capitalized. Capitalized, not capitalized, capitalized, capitalized. Right? You just go through, you want to get out of there. So you're just what the words are doesn't really matter to this task in the sense of semantics. You might go a little bit deeper as the experimenter at another condition where they ask what the that whether the word presented rhymes with something. Does train rhyme with rain? Well, it does. But the rhyming thing too is a deep semantics. That's just kind of a middle level. It's a kind of morpheme level, an auditory level. You with me? So a little bit less deep than the extreme, but still a little deeper than just capitalization. Or I might have another condition where you would say, does this word fit into a particular sentence? So I took the blank to work today. Is that sensible? Took the train to work. Yes, that's sensible. You might even have, you can imagine even deeper things, personal things, for example. So it turns out, this is, you've already guessed the end of this story, right? Is that these guys, this condition, despite all these words being the same across all the conditions, in this condition, you get forest recall. In this condition, you get a little bit better. In this condition, you get the best. Because, again, this is supposed to be shallow, deeper, and deeper yet. So their argument is that how that encoding gets done drives your ability to get the thing back out of long-term memory. Okay, so that's this, again, shallow to deep structure idea. Okay, so you can encode information in lots and lots of different ways. Generally, encoding things in lots of different ways increases your ability to recall them. So it's kind of like a shotgun approach to memory. Not sure it's best for things like studying, because you only got so much time, and variabilities can be hard to generate. So deep processing is probably better because it does a lot of other nice things too. But in general, encoding variability helps. And again, because you're supposed to now have a whole, like you think about it as having like a whole bunch of hooks hanging off the thing when you go to get it, right? Well, I've encoded it as a rhyme. I've encoded it also as a fact about whether it's a transportation device. I've encoded it also as a something else, right? And so those are all sitting there, and depending on what cue comes in, a different hook is grabbed essentially. Right? So that's why, in theory, variability works. Okay, so the lesson from this body of work is that the more ways a memory is encoded, the greater the likelihood of retrieval. So that also works to some extent. So one thing that this would recommend for studying is you could try to encode things in a lot of different ways. You could try reading the textbook. You could try reading the textbook under various conditions. You could try remembering the lecturer's voice during the lectures. I'd try to recommend that one. You could try drawing pictures about the material. Works in some cases. I'm not sure how you're going to draw some of these pictures, depending on map or something you're going to draw. Maybe there are some things to be drawn there. But again, the idea is to kind of approach encoding of the concepts from all these different angles. So this whole body of work gets kind of summed up in this thing they call the encoding specificity principle. And it's a strange and wonderful principle that people in memory research love. So, but if you know about this and you go to your cognitive psychology class, they will be very impressed. So the encoding specificity principle says that the ease of retrieval depends on the match between the information present at encoding and the information present at retrieval. What does that mean? If the theory is that to the extent that the surrounding context at learning and the surrounding context at retrieval or test are the same, right? If they're to the degree that they're the same, retrieval is likely to happen. To the degree that they're different, retrieval is increasingly less likely to happen. So why would that be? Well, they say, well, that's because when you form a memory, you're forming a representation of the thing in its context. And the context then acts as a set of cues that allows you to get to the thing. They think this is like the keys to understanding memory. This is the big principle that's supposed to drive huge number of results. Let me give you some examples. I realize that's kind of weird. So here's an example of how we usually structure things, which is contrary to this principle in the sense that it's not optimal way to structure things, given what this principle says. You usually study not here, at home, in the library, someplace that isn't in this room, right? And then you test here. So the context in which you're studying and the context in which you're taking the test are always different. And that is very clear, but so there's a lot of work that shows. I mean, it doesn't doom you to bad scores or anything, but it slightly decreases your likelihood of getting really good scores. Because those cues somehow are tied up with the information about the course from when you're doing the studying, right? So if you're sitting there on your bed, with your legs up, and there's different lighting than this, you're comfortable, you're in a different posture. Maybe that's not a good. Let me not recommend that. You're sitting there in the library at a desk under harsh light, not sleepy, and you're going through your flashcards. Not Quizlet. But still, that's not the same as here. Right? So you come in here and things are different. And that difference is supposed to kind of get in the way of recall. Okay? So that's one example, kind of counterexample in terms of optimality. One very dramatic and kind of showboaty even example of this. It's a very famous study done by Godin, don't know what happened to them, and Badley, the very famous Badley, where they did a study test design where half of the time people are studying and testing on land, and half the time they are literally studying and testing underwater in scuba gear. Okay? I mean, it's a total showboat move, right? But anyway, so literally half of the subjects are studying on land at a desk in a normal kind of situation. But the other half of the subjects are studying, okay, in scuba gear at the bottom of a pool. Okay, so you got those two groups. And then they further split those two groups. So half of the study on land group test on land. The other half test underwater. Likewise, half of the study underwater group test underwater. The other half test on land. With me? Goofy, right? But what works, and why it's kind of why they did it, I kind of dinged them a little bit for showboating, is that underwater and on land is so totally different in these situations, right? I mean, it's like, okay, so I'm weightless and I'm breathing through a tube, right? I got this thing pressed on my face, right? That's a totally different physical situation. And it turns out, of course, otherwise I wouldn't be telling you about it, that the matching groups where study and test is done in the same condition, remember the best, right? So if I study on land and I test on land, or I study in water and I test in water, those are the best, right? The mismatches are not good, generally speaking. Okay, so it kind of supports it, and it actually supports it really nicely. Right, so again, that's the encoding specificity principle. But there are weird things, right? I mean, what difference does it, if I'm trying to remember which list of words, why does breathing through a tube matter? Why does that match that? Not so clear. And they say, well, it's just content. That is the stuff that cues are made out of. It's the context of the situation. final example is a favorite one from a friend of mine who's a memory researcher, and she, like I think everybody, would sometimes struggle with people's names. And she said, "Oh, there's research about this." Like, what do you mean? She's like, "Well, it turns out that there are studies where if you can't remember somebody's name, but you know that you knew it or know it, I guess, the thing to do is to walk right up to them as close as you can get. I mean, not this close, reasonably socially close, and expect the name to be there." Like, what are you talking about? She says, "Yes, that you are reinstantiating the cues, undoubtedly, where you learn that person's name, right? You went, you met them. So reinstantiate that situation, and you're most likely to remember their name." Sometimes this works for me, sometimes I just get embarrassed, right? But you see the idea, right? So the idea is it's not so much just seeing them at a distance, it's actually having the whole set of cues reinstantiated and then the name. So that's another example of this principle of work. Okay. So this is all kind of nicely exemplifies the encoding specificity theory. Another related idea is the idea of state-dependent memory, which is also explained by encoding specificity memory. It's kind of an older phenomenon. So state-dependent memory means that the state of you, when you are making the memory, if it matches the state of you when you're trying to recall the item, you'll get better memory. Okay, so if you learn somebody's name right after, I don't know, right at the end of your 400-meter track workout, right, and your heart rate is up and your breathing rate is up and you're a sweaty mess, right? That's the state of your physiology at that point. You will, according to this idea, you will remember that person's name better should you try to recall it in that same physiological state, right? And that works for things like physiology, but it also works for things like mood and alcohol and so on and so forth. Okay, so there is some evidence for that too. And again, it works with the encoding specificity principle because everything is context, including your body's physiological state. All right, the final sort of practical thing I want to tell you about in memory is the idea of distributed versus massed practice. So this is the very kind of engineering level idea that if you try to learn things all at once, a large set of things all at once, as opposed to learn things spaced over time, you may get different results. So distributed is learning things over some spaced study sessions, actually. Massed is essentially cramming, like trying to get everything in all at once. And I know I've heard over the years people say, "Well, cramming always works for me." That's how I do it. And that could work for an individual. I'm not saying it doesn't. But in general, distributed practice tends to work better than massed practice. So people have wondered about that, thought about that. So again, distributed practice is learning the material over lots of relatively spaced sessions. Massed practice is learning the material in one shot or relatively few shots. So a classic study, these guys controlled all the things you want to control. They had people learning 20 French words. The English speakers trying to learn French words. They all had an equal amount of study time. And then they broke the group up so that one of them did a massed session, that is one session, all 20 words. And the other, let's say all equal study time. And then that same amount of time distributed over 3 sessions. Make sense? So very straightforward study, and they get these beautiful results. So everybody on the initial test gets almost, well, not really quite perfect, I guess, right? A little, right around 16, and these aren't really different from each other. This guy is spaced. This guy is spaced by the man. And this is just the average number recalled. Okay, so the idea here is that this is the initial test, and this is just like right after we did the studying, how many can you recall? Okay. And then later, we have a final test, and you can see that the people who did spaced or distributed practice, right, do better than the people who did massed practice. Right, and so so there are dozens and dozens of these studies and various and sundry perturbations on them and combinations. So, but generally speaking, this seems to be the case. Having things distributed across multiple sessions is really like it's not just like little effects, like practically superior, worth trying to do. So this has been shown in motor learning, it's been shown in language learning, and it's been shown in sort of the more everyday academic kind of content as well. So there are a bunch of other things that people in this kind of realm who are kind of like memory theory meets, I don't know, it's not quite education, but meets like practical implications for testing have found. So one thing that, and if you've been in to talk to me, I'll probably have said almost these words. The feeling of familiarity that one gets from reading or from kind of passing the material kind of by yourself turns out to give you a false sense of knowing. So that's what I mean by familiarity is not your friend. So if you read a chapter, you'll feel like, well, I'm familiar with that now. Yes, I've heard those words. But that level of knowing turns out not to be a level of knowing that's sufficient to do well on a test about knowledge of those concepts generally. And so that's why familiarity is not your friend, right? You actually have to recreate study conditions. Which is the next one. So self-testing helps tremendously. So what you want to do is create a situation that's as much like the actual exam as possible as part of your study routine. It doesn't have to be your whole study routine, but as part of your study routine. So that kind of self-testing really helps people because you actually just learn how to do the test and then you take the test and it works. So how one studies and how one tests, that relationship matters. So if you're going to have an exam which is like essays, your studying should be readying you for essays. You should write like little essays before the essay exam. That will help a lot. Doing like the flashcard technique that I've been pushing around in here will not help you as much. Better than nothing, but won't help you as much. So getting ready like for that particular test with that method will help you the most. So if it's going to be a recall test, then practice with recall. If it's going to be a recognition test, practice with recognition. All right. Jeez, I'm so long-winded. How are we ever going to get through this course? So the last thing I want to tell you about is some organizational things about memory itself. Less directly related to studying things. But one of the weirdo issues in memory is how could it possibly be organized in a useful way? Since I keep adding things willy-nilly, right? It's like, how could you always have room on how do you know where it goes, right? You get this new piece of information, and yet somehow you put it, right? So I learned something new about cats. And somehow your brain must find a way to put it with the other cat information, right? And hook it in properly to all the other, right? How does it get hooked into that network properly? It's amazing, right? It's like having a library book come in and it automatically finds its place in the index and goes to the right shelf in the right place. And right, but it's even more than that because somehow the contents are connected to the other contents in the library. It's quite miraculous. So people have been interested in that as a problem. One of the ways, it doesn't really solve all these problems, but we'll talk about it this way, is to think about it as a network, right? And I keep kind of coming back to that. So a node in the network then becomes an item in memory. It becomes a thing in memory. And so that seems like a reasonable idea. So let's think about this as a somewhat cheesy, put it to work, network. So I think it still is. Tide is both a laundry detergent, and tide is also a natural phenomenon that has to do with the moon and the ocean and all that. You know about that. You know about laundry detergent one too. And the interesting thing here is that this word has to be part of both these networks. So that's kind of strange. And people in psychology, being kind of moderately clever, have played around with this, right? So what if I introduce this tide idea, word, but I do it in a context that clearly implies laundry detergents? Right? Do I get activation over here so that now words like waves and moon and ocean are more easy for you to pick up out of text or something? Well, it turns out it does, right? So and this brings us to the notion of spreading activation theory, because anytime something is activated, so here are now being overworked term tide, anytime this is activated, its activation somehow spreads out to the other things it's connected to. So just saying the word tide does activate lots of things about the ocean and the moon and so on and so forth. But it also activates things in this unrelated way over to detergents and vice versa. And so that's this idea that the kind of the arousal of the node spreads out to its neighbors is a very powerful one that people have tried to use to explain why meanings get hooked together. So this interestingly relates all the way back to Aristotle, the contiguity, similarity, and contrast. So you can get all these effects out of these kind of networks. All right. The last thing I want to show you is a little bit of an old-timey, but I think still interesting network. So this is a network of creatures. And what we're seeing here is that they want the network here to be hierarchical. So here we have animals at the top, and then types of animals, birds and fish are both types of animals. And then just examples of fish, shark, salmon, canary, and ostrich. And in this idea, you can see that animals have properties, right? And we all know that animals have properties, and that birds and fish have properties as well. And that there's this very strange thing where there's cognitive economy, where an animal at the top of the network, right, has sort of the most general things that are animal common, animal defining even maybe. Likewise for birds. And then we have the particular things of each individual instance of these types, right, have their own properties. So this is a way of representing all this information in something that is non-redundant. Right? So this makes some predictions about how you might move about in a network to know about these properties. All right, I've got to let you go there. Thanks for your attention.